Okay, so today's lecture, we're going to look at long-term evolution or LTE. Angren was supposed to give this lecture, but he was unable to make it today, so he has asked me to give this lecture for him. So what are we going to cover? Well, we're going to first start off by looking at the evolution towards LTE, and then an overview of LTE. Okay, one of the important feature that LTE offers is something called spectrum flexibility, and we'll have a look at that. We'll also have a look at how LTE can adapt its performance to the state of the physical layer. Then we're going to look at LTE multiple access, but before that we'll have a look at LTE network architecture. And in multiple access, LTE uses something called OFDMA in the downlink, and it uses something called single carrier FDMA in the uplink. So we'll briefly have a look at these two mechanisms as well. Okay, in terms of evolution, I think in this subject we've sort of covered most of these technologies. We started off by looking at release 99 UMTS wideband CDMA. So we looked at how wideband CDMA works in the fourth lecture. We looked at the network architecture of UMTS in the third lecture, and so forth. And subsequently, I think 2 weeks ago, you had a look at both HSDPA and HSUPA, release 5 and release 6. And then in release 7 came the introduction of something called Evolved HSPA, where on the downlink something called MIMO was used along with the IP multimedia subsystem, and this allowed better services to be offered to users. And the next step after release 7 is LTE, and between release 7 and LTE there's going to be further enhancement. So this is LTE is in the process of being standardized now, and some test networks have already been in operation, but hopefully in the next couple of years, if the financial situation doesn't get worse, the operators will start to roll out LTE. Okay, now why was the need for all of this evolution? Well, we knew there were problems in GSM. We came up with GPRS. There were problems in GPRS. We came up with wideband CDMA. But still there were problems. Okay, so further evolutions and enhancements were followed in order to make it more competitive, because there are other technologies that are coming up in the market, WiMAX being one of them. So in order to make this the technologies in this evolution passage to be as competitive as WiMAX, they had to make improvements, continuous improvements to technology. We've already talked about the evolved HSPA, and this essentially enables with at a low cost, it can facilitate the evolution of the existing HSPA network. Okay, and LTE is the one that we're going to look at today. So LTE is going to give us improved performance in a wide range of applications. Okay, if you go back further, I think you would have seen all of these technologies by now. The technologies on the top there, those ones represents the 3GPP one, and the ones at the bottom are essentially 3GPP2. So as time went on from first generation to second generation GSM, and then to wideband CDMA, and then HSPA, and then to LTE. And on these other technologies which are now being looked after 3GPP2, you had CDMA, EVDO, and then hopefully it is envisaged that eventually even these technologies can evolve towards LTE. Okay, what is the main reason for this evolution? Well, it is data rates. Okay, with time, if you look back to GPRS rolling out in 98 or 2000, it could give packet switch data rates of 40 kilobits per second with wideband maximum, and with wideband CDMA maximum probably about 384 kilobits per second. The HSPA maybe 3.6 megabits per second, and so forth. So the projected is that by the time we get to LTE by 2011, data rates of about 100 megabits per second should be possible. And that's what the standard bodies are working towards. Now it should be also possible to go beyond 100 megabits per second, because one of the things that we can add on to LTE is the technology called MIMO. So in this slide here, if you take MIMO and you increase the number of transmit and receive antennas, you can see that every time you add more transmit and receive antennas, the data rate improves. Okay, so for example, if you take HSPA with standard 14 megabits per second using a 5 megahertz carrier bandwidth, if you were to employ two transmitters and receiver, two transmit antenna and two receive antennas, you can push that from 14 megabits per second to 42 megabits per second. And then and this is part of the HSPA that we talked about earlier. And if you go further and you put 4 transmit antennas and 4 receive antennas, then you might be able to get even higher data rates. So here you can get up to 80 megabits per second. Now with the basic LTE, we'll start off at about well, initially most of it is going to be based on the 10 megahertz carrier bandwidth, but eventually it is planned that you will move down to a 20 megahertz bandwidth. So with a 10 megahertz carrier bandwidth, LTE is supposed to offer about 25 megabits per second. Doubling the carrier bandwidth will essentially double the data rate to 50 megabits per second. And again, if you double the number of antennas at the transmitter and the receiver, you'll be able to get about 100 megabits per second. And if you go further than that, you can get maybe up to 200 megabits per second with a combination of LTE and MIMO. Okay, I think you've seen this slide before with Sandrasegaran. Okay, it shows how Telstra is planning to roll out their networks. They've already gone with HSDPA, and now they're testing and rolling out some HSPA networks. So they have it on both downlink as well as uplink, and they're planning to move further. By 2011, Telstra has a plan to start putting MIMO, and then they're also planning to do some test networks with LTE. So some of the operators in Australia are planning to do this in the next couple of years. This is all assuming this current financial credit problems do not get worse, because at the end of the day, Telstra has to borrow money from banks and other investment community to roll out these networks, and if it becomes harder and harder to loan money, then these rollouts will all be pushed back until the situation is better. Okay, now how did these most of the LTE documents based on 3GPP documents. So essentially, first a feasibility study was done, and there were 4 working groups, and each working group focused on one specific area. So there was one working group focusing on physical layer aspects, another working group focusing on radio interface protocol, another one the radio access architecture and interfaces, and so forth. And you had different organizations, companies that were editors of these working groups. So for example, this one here was edited by NTT Docomo because they were probably the pioneers in the use of this technology. And then other companies like Nokia, LG were involved in radio interface protocol aspects, and so forth. And in terms of each individual component, different components were given out to different manufacturers. So Node B was looked after by Ericsson and so forth. So these working groups did feasibility studies on various aspects of LTE, and they came up with a report, and this report was then used to come up with requirements. Now the requirements document are pretty complex. Okay, I think there's a 30-page document that has so many requirements for LTE, and most of the documents, when I looked at it, they all specify in terms of how LTE should perform with respect to HSPA. Okay, so how many times better should it be? Should it be 3 times better or 4 times better, and so forth. So those were the initial documents. Now all of these documents are all available on the web, so you can go and have a look at them on the 3GPP site. Okay, so all the as I said earlier, all the LTE standard specifications are downloadable from this particular site. The specifications have been classified into 5 groups: 36.1, 36.2 up to 36.5. Each one of these group focuses on different aspects of the LTE standards. So the 36.1 standards focus on equipment requirements, terminals, base stations, repeaters, and so forth. Okay, so the next thing that we'll have a look at is an overview of LTE. Okay, LTE is probably quite a complex system. So I've tried to simplify this as much as possible without going into the details. So if you look at some of the initially I'll focus on some of the key features of LTE, and then I'll go into each one and try and explain it a little bit more in detail. Okay. Now, one of the things about LTE, which is quite different from the existing mobile systems, is that it uses a different multiple access scheme on the downlink and uplink. So on the downlink, it uses something called OFDMA, and on the uplink, it uses single carrier FDMA or SC FDMA. And in both of them, something called a cyclic prefix or CP is added to minimize the effect of the transmission medium. Another feature of LTE is the fact that it uses link adaptation. So in link adaptation, what you're doing is you are changing the modulation scheme and the error coding scheme to match the condition of the transmission link between the mobile and the network. So there are different modulation schemes that you can use. You can use QPSK, 16 QAM, 64 QAM. So when the channel conditions are very good, you would use 64 QAM, and if the channel conditions get bad, you would go down to QPSK. Okay, and then there are also different types of error coding codes, convolutional codes, turbo codes that can be used depending on the degree of protection that you want. Another feature of LTE is something called MIMO, and I briefly talked about this earlier when we were looking at evolution. And this idea is essentially the idea of using multiple antennas at the transmitter and the receiver. So you can have something called 204 multiplied by 204. So that means you could have either 2 transmitters or 4 transmitters at one location, and either 2 or 4 receivers at another location. So this essentially, by using MIMO, you're able to obtain a much higher data rate. The other good feature about LTE is that it can work both in the FDD mode and TDD mode, and it can switch between these modes as well quite easily, because they've sort of decided that the frame structure that they're going to use is going to be quite similar, and we'll talk a little bit more about this later on. In terms of error control, it also provides hybrid ARQ mechanisms, so that when frames come in error, how do you overcome the effects of those errors? It provides mobility control, rate control, and so forth. So what sort of technologies? So if those are the basic ideas behind LTE. What sort of technologies are used? Well, we've already said that it uses, it's based on the downlink. LTE uses orthogonal frequency division multiplexing. Have you come across OFDM in any of your subjects so far? No. Okay. It also uses something called frequency domain equalization. On the uplink, it uses single carrier FDMA. It uses multi-input, multi-output as a means of improving the data rate. The other thing that it does is the resource scheduling. Packet scheduling is essentially based on the carrier channel condition. So that's another technology that is built into LTE. And there's also something called fractional frequency reuse, whereby you could have the way you use your reuse your frequencies is quite different in the center of a cell and at the edges of a cell. Okay, so we'll focus on each one of these features that we talked about. So the first feature that we're going to look at is LTE Spectrum Flexibility. Now, LTE is going to be rolled out in many different parts of the world. And in many different parts of the world, the spectrum regulations can be quite different. And also the availability of spectrum can also be quite different. Now, this was one of the mistakes that was made with wideband CDMA, was that it specified a very rigid frequency band. And if that frequency band was not available, then you could not roll out a wideband CDMA network. That's basically what happens in the rollout of wideband CDMA in the USA, because the existing bands that were specified for wideband CDMA were already used up for other purposes in USA. So what they decided with LTE is that it must be flexible enough so that whichever part of the world you go to, and with whatever frequency bands that are available, you should be able to roll out a basic LTE network. Okay, so this is what is meant by the fact that LTE must support the international wireless market and regional spectrum regulations and spectrum availability. So in different geographical areas of this planet, the mobile communication, the spectrum that is used for mobile communication could be different bands, could be using different bandwidths, and it could also be using different duplexity. Okay, so you should by now know the difference between frequency bands, the bandwidth, and the duplexity. And LTE has been designed in such a way that whatever is thrown at it, whichever part of the world you go to it, it should be able to cope quite well with different situations. So how does it do that? Well, essentially, the LTE spectrum flexibility has been specified such that in different size spectrum, starting from 1.4 megahertz up to 20 megahertz, different size spectrum allocations, and whether you're looking at the 850 band, the 900 band, which were the GSM 900 bands, or the 1800, 1900 band, which were from the GSM 1800 bands, or the 1700, 2100 bands, or the 2.1 gigahertz band, or the 2.6 gigahertz. In all of these bands, LTE should be able to operate. Okay. Another aspect that is associated with spectrum flexibility is that you want to be able to have something called smooth spectrum migration. So maybe you already have a GSM network and you have some GSM frequency bands. And what you could do is slowly you could convert those existing GSM bands into LTE for use for LTE. Okay, so you don't have to go and purchase new spectrum from the government to roll out an LTE network if you've got existing bands in those bands that I talked to you about. Okay, there's also a plan to move migration of other spectra, example TV bands. Okay, so you know that with TV we are slowly moving out of analog TV and we're going into digital TV, and when we do that, a lot of the analog TV bands are going to become free, and it is hoped that even some of those TV bands could be used for transmission of LTE based mobile communication systems. Okay, now in terms of bandwidth, many possibilities. The lowest bandwidth is supposed to be 1.4 megahertz, then 3 megahertz, 5 megahertz, 10 megahertz, 15 megahertz, 20 megahertz. These are all bands that are the bandwidth that can be used for LTE spectrum. Okay, so there's a word that you will come across, and it's called bandwidth agnostic. Okay, so 3GPP has defined LTE air interface to be bandwidth agnostic because it essentially allows air interface to adapt to different channel bandwidths with minimal impact on system operation. Okay, so if you have only 1.4 megahertz today, you use 1.4 megahertz. In 2 months' time, if you can get 3 megahertz, then without making any major changes to the system that you have, you should be able to use the higher bandwidth and so forth. So initially, as I said, LTE can be deployed all the way from a bandwidth of 1.4 megahertz to 20 megahertz. The 1.4 megahertz can be used for initial migrations from GSM, and the 20 megahertz represents the high end, and that sort of bands are going to be not going to be available for quite some time. In each one of these bands, what the LTE standard has specified is that you are dividing each band into a number of subcarriers with a 15 kilohertz spacing. So whether you look at the 1.4 kilohertz band or the 20 kilohertz bands, it's divided into 15 kilohertz subcarrier spacing. So that means obviously you're going to have more subcarriers at 20 megahertz compared to 1.4 megahertz. And this subcarriers form the basis of defining what is allocated to a user. So obviously, as I said, if you're at 1.4 megahertz, the number, okay, there's something called a resource block. So I need to explain to you what a resource block is. So the thing that is allocated to a user is something called a resource block. So this is a very important term. And you should probably make a note of it or highlight it on your slides or underline it, because the resource block is the thing that is allocated to a user, both in the uplink as well as in the downlink. So what is a resource block? A resource block is essentially 180 kilohertz wide and lasts one time slot, and one time slot is 0.5 milliseconds in the OFDM, in the LTE standard. So if you're looking at if you look at 180 hertz wide radio, not radio block. Remember, radio block is something that comes from GPRS, so that is quite different to resource block. Resource block refers to a group of frequencies and also one time slot. So a resource block, so at 1.5, the 1.4 kilohertz, megahertz, 1.4 megahertz bandwidth, which is the smallest bandwidth in the LTE system, you can have up to a maximum of 6 resource blocks. So because we said earlier that that the subcarrier in LTE has a 15 kilohertz spacing, within one radio, within one resource block, you can have 12 subcarriers. Okay, and this table here shows you the maximum number of resource blocks that can be provided in different bandwidths. Obviously, the higher the bandwidth that you use, the higher the number of resource blocks. The higher the number of resource blocks, the higher the number of users that can simultaneously transmit in that band. So if you look at it from another point of view, okay, this diagram here, it's important that you understand this diagram as well. On the vertical axis, you've got frequency. So on this axis here, you've got frequency, and on this axis here, you've got time. Okay, we just now said that subcarriers are 15 kilohertz, and we said that a resource block spans 12 subcarriers. So if you go from here to here, you've got 12 subcarriers of 15 kilohertz each to give you a total of 180 kilohertz. Okay, so that's in the frequency axis. And on the time axis, this length here corresponds to one slot of 0.5 milliseconds. So this represents, the resource block is a block that is allocated to a user. Okay, so user gets multiple subcarriers for one time slot, and in that they can transmit across those various subcarriers. Now inside, if you go further into a resource block, this is the same diagram as the previous diagram. You can have something called a resource element. So resource element, each, you think of that resource block as a matrix made up of a number of subcarriers and one time slot across there. Then each square is referred to as a resource element, and in those resource elements, that's where you place your modulated symbols. Okay, again, another the same concept drawn a different way. Okay, so there on this axis, okay, so this is the orange pattern here. The orange grid here represents one resource block made up of 87 resource elements, because we've got 12 subcarriers and we've got seven OFDM symbols. So multiply the two, you get 84 resource elements. And in each resource elements, if you are using QPSK, you'll be transmitting 2 bits. If you're using 16 QAM, you'll be transmitting 4 bits. And if you're transmitting 64 QAM, you'll be sending 6 bits on it. So essentially, you're transmitting one symbol, and in each one of these modulation scheme, there is a mapping between one symbol and bits. Okay, so in QPSK, one symbol corresponds to 2 bits. In 16 QAM, one 16 QAM symbol corresponds to 4 bits, and so forth. Okay, another aspect associated with LTE spectrum flexibility is to do with duplexing. Duplexing is how you differentiate between the uplink transmission and the downlink transmission. So in LTE, you can have 3 possible duplex transmission. You can have the standard FDD, where the uplink and the downlink are separated in frequency. Then you can have the TDD mode, where you use an unpaired spectrum. So in parts of the world where you can only get unpaired spectrum, TDD might be a good solution. Okay, because in this solution you are either transmitting uplink or transmitting downlink, but not both at the same time. A third possibility, that's the one that's shown in the middle here, is referred to as a hybrid FDD-TDD mode. So in this one, you using a combination of FDD and TDD. So what you're doing here is your receiver is either transmitting uplink or receiving on the downlink, but it's not doing both at the same time as opposed to FDD. So basically, this scheme is supposed to reduce the complexity of a UE, because now your user equipment does not have to transmit and listen at the same time, which implies a more complex user equipment. Okay, so LTE can essentially operate in both paired and unpaired spectrum using technologies that support either FDD or TDD or a combination of the both. And in FDD, you can either have full or half duplex mode. The half duplex mode is supposed to reduce the complexity of the UE. Now one of the important things, if we can reduce the complexity of the UE, we can make the UE cheaper, and that means that the technology can be rolled out much more easily. Okay, the next aspect is that by using this, we can also make LTE fit any arbitrary spectrum allocation. Obviously, if you have FDD, if you have paired spectrum available, go for the FDD mode. If you only obtain unpaired spectrum in some country, then go with the TDD mode. Now, the other thing that they have made for the ease of moving between FDD and TDD, they have made sure that the frame structure that is used is the same for different bandwidths and similar for FDD and TDD. So whatever bandwidth that you have, whether you have the 1.4 or the 3 or the 20 megahertz bandwidth, or whether you're using FDD or TDD, the LTT uses the exact same frame structure. So that is quite a useful thing, because if you go back to some of the systems that we've seen before, you know that across even FDD and TDD, there's quite a big difference. So it's not quite easy to change over from one to the other. Okay, now this is because we just now talked about frame structure. I brought in a diagram here which shows the frame structure that's used for both FDD and TDD. You can see that they are quite similar. They both, the radio frame in both FDD and TDD are 10 milliseconds. There is a slight difference because in the FDD mode you've got one time slot for 0.5 milliseconds and you've got 20 of these slots, whereas in the TDD mode the time slot is still 0.5 milliseconds, but you have something called a subframe which is made up of 2 time slots, and the number of you could be transmitting on the uplink for a portion of the time, and you could be transmitting on the downlink for a portion of the time. So the number of subframes that you have is quite different from TDD to FDD. Okay, now one of the things I told you earlier is LTE. One of the things that was decided because of the nature of mobile communications that there should be a lot of flexibility in the spectrum. So imagine that you are rolling out a GSM. You had a GSM network and you want to migrate part of the GSM network to LTE in the future, maybe in 2010 or 2011 when these networks are supposed to roll out. So essentially you might start off with a GSM system which may have a number of 200 kilohertz carriers. So because you're dealing with first solution might be, okay, we take a couple of these GSM carriers and maybe we introduce LTE in the 1.4 megahertz band as shown in yellow on this particular diagram, and on the remainder of the GSM bands we continue to operate a GSM network. Okay, and if the concept picks up and more users want to use LTE, then you might expand it. Okay, so obviously as you increase the band, the data rates are going to increase. So here LTE has now been expanded from 1.4 megahertz to 3 megahertz, and then as time goes on further you might go up to 5 megahertz or 10 megahertz, and all of these increases will provide users with much higher peak data rates, and also capacity. The number of simultaneous users that can be supported will also increase. So this is what is meant by the fact that LTE has been designed in a flexible manner so that existing GSM bands, for which operators have paid a lot of money for, can be reused for the rollout of LTE network. And then you will also have handsets that will be dual mode handsets which can work either in the LTE band or the GSM band. In terms of the, we talked about some frequency bands that are used. Okay, here I just wanted to show you these bands. So those bands that we talked about earlier, I gave in one of the earlier slides, I listed some of the frequencies that are used for LTE. Most of these earlier bands, which were the 800, 900 bands, the 1800, 1900 bands, the 2100 bands, and so forth, most of these are going to be based on FDD. And then the other bands that are below here are the ones that are going to be used for TDD. And some new bands are also going to be made available for the use of LTE in the future. Okay, so if you were to summarize what was in the previous slides, it is hoped that eventually these FDD system, the HSPA and so forth that operate in these kind of bands, the 450, 800, 850 and so forth, these will be used for LTE in the FDD mode, and the LTE in the TDD mode will mostly be used in the 2.1, 2.3, 2.6 gigahertz bands. Okay, so again, this is a summary that shows the different bandwidths that you can have, and how many subcarriers that can how many subcarriers. Remember, we said that there is a 15 kilohertz subcarrier spacing. So how many of these subcarriers can we have in each one of these bandwidths or spectrum allocations? Okay, another thing that I talked to you about earlier was the fact that LTE displays a lot of is supposed to display a lot of adaptive behavior. Okay, and we're going to talk about that now. So what does that mean? Okay, so here's a diagram. You've seen a diagram similar to this when you did the HSPA. As far as the user is concerned, this could be the channel quality that is being measured by two users. So you've got a user blue and a user red there, and the blue line represents the channel quality that is being observed by the blue user, and the red line represents the channel quality that is being measured by the red user. Okay, now if this is the situation, if these are the measurements, then ideally what we want to do is, when the channel quality is good for any one user, you want to transmit as much data as possible for that particular user. So you can see that here blue user transmits the portion that is quite dark here, that represents the portion where the blue user is transmitting. Then the red user then transmits because the red user's signal quality is better, and so forth. Now you can take this situation, this is a two-dimensional situation, and you can expand that to a three-dimensional situation. So here, this diagram here represents a three-dimensional diagram where you've got time on one axis and you've got frequency on another axis. Okay, so this one only represents the variation of channel quality with time only. Okay, but there is also a variation of channel quality with frequency. So if you look at this, the yellow here could be the channel quality measurements that is being made by user 1 due to fading and other radio propagation mechanisms across many different frequencies, and also at many different instances of time. And the blue represents similar measurements being made by a second user. Now what you want to do is, if you look at this diagram, when one is higher than the other, whenever the blue is higher than the yellow, you want to try and allocate blue as much resource. So when blue is higher than yellow, allocate all of the resources or most of the resources that you have to the blue user. So that's basically what's happening in this particular. If you look at it, remember in OFDM you've got a number of subcarriers. So, and we have the idea of a resource block. So these squares here represents a resource block. Remember, a resource block is a number of subcarriers and across one time slot. So here what's happening is, in this instant of time, if you look at this instance of time here, the first resource block is being allocated to the blue user. The next two resource blocks are being allocated to the yellow user. The next resource block is being allocated to the blue user, and so forth. because primarily you are looking at the different frequency bands that you have available and allocating the best to the best user, allocating each resource block to the user that has the best measurement on that particular resource block, or the best channel quality on that particular thing. So you can see that from time to time it can vary. Okay, on the next time instant, the allocation of resource block is quite different. Okay, in the second instant of time, the first two resource blocks are being allocated to the blue user and the remainder for the yellow user and so forth. Okay, so essentially this is a three-dimensional version of this diagram that you saw earlier in HSPA. So one of the things that LTE uses is something called channel-dependent packet scheduling. Okay, so what is scheduling? Well, scheduling is all about dividing the resources that you have, the resources that you have to provide to the users, and allocating these resources to different users who have data to transfer. Okay, so you have to do scheduling both in the uplink as well as in the downlink. In the downlink, you have a number of packets waiting to go to different users, and in the uplink, you've got different users who have packets to send to the node B. Okay, so in LTE, the scheduling time instant is called 1 millisecond. So scheduling time period is 1 millisecond, and this is applied in both the uplink as well as the downlink. So I talked to you about channel dependent scheduling. So basically in channel dependent scheduling, those users who have good channel conditions are allocated more of the resource. So essentially what you're doing is allowing the transmission on time and frequency those users who have good channel conditions. Now by doing this, in some way, assuming that all users have equal probability of getting good channel conditions, by having something called channel dependent scheduling, the resources that you are using, you're using it more effectively. Because if you are allocating resources for users with good channel conditions, then they have to use less overheads in terms of error. They can use a high order modulation scheme so they can get their data quickly and so forth. So that is what is meant by this point here. Okay, it says here fewer radio resources and less time are consumed for any amount of information to be transferred. So this mechanism requires that users are continuously reporting the channel quality. Okay, so this is called CQI, or channel quality indicator, to the node B, which then selects the user and the data rate based on the instantaneous channel quality. So this process of reporting channel quality back to the node B or the base station can be quite an expensive process. Because remember, if you've got many mobiles, they're all reporting these measurements. So there are different mechanisms that they've come up with to try and improve that reporting mechanisms. Now, it has been found that when you have services which are using small payloads and services that have regular packet arrivals, for example, things like VoIP, where you've got regular packet arrivals, the percentage of control signaling that is required might be disproportionately large relative to the amount of user to be transferred. Okay, so this channel dependent scheduling is good for bursty traffic. Okay, when different users suddenly have a burst of data to transmit and rest of the time they're quiet. But when you have a situation where users are regularly transmitting packets, basically any circuit switch, the previously circuit switch kind of, or real-time circuit switch services in which you have regular arrival of packets, and usually with small payloads. Okay, so for those kind of services, this kind of scheduling is not good because of the fact that the amount of percentage of control signaling that you require is quite high. So there was another scheme that was proposed, and that is called persistent scheduling. So in persistent scheduling implies that radio resources are allocated to user for a given set of subframes. So each user who has data payloads that are small and are regular might be allocated a fixed number of subframes until their status changes. So two types of scheduling, channel dependent scheduling and persistent scheduling, are specified for LTE. By the time this LTE actually rolls out by 2.11, there might be other scheduling mechanisms as well, because a lot of these things are being researched. Another thing that has to happen in LTE is called link adaptation, and you've already seen this happening. The quality of the link between the base station and the mobile is continuously changing, and because it's continuously changing, you need to adapt to this change in link quality. So link adaptation techniques are used to improve the instantaneous channel quality, and it is only performed in the time domain as opposed to packet scheduling, which is done in both time as well as frequency. Link adaptation involves selecting the best modulation and channel coding scheme based on current channel conditions. So if the channel conditions is poor, you drop down in modulation from maybe 64 QAM to 16 QAM to QPSK, and maybe the error control, you use stronger error control coding, so the percentage of overheads that you're going to be transmitting is large, but at least you'll be able to correct the errors that are occurring due to the poor link that you have at present. Okay, so again, the type of modulation scheme and the type of error coding scheme that you use will determine the data rate, the effective data rate. Okay, because effective data rate or throughput is based on the error probabilities and so forth. Okay, the next thing that I want to have a look at is packet transmission. Whenever packets are sent across any wireless network, you're going to get errors, and errors occur due to noise, due to interference, due to fading, and so forth. So how do you overcome the effects of errors? Well, the two basic techniques in telecommunication are forward error correction and backward error correction. So in forward error correction, what you do is you put extra overhead, quite a lot of extra overheads, so that the receiver is capable, based on the information it receives, to correct the error. Okay, and there are a number of forward error correction schemes, but the more complex forward error correction scheme that you use, the more the overheads that you're going to put into the transmitted data. Backward error correction schemes are schemes in which, when you detect errors in the received signal, you go back to the transmitter and say, look, can you transmit this frame again, because the frame you sent me was in error. Okay, so these schemes are referred to as also as retransmission schemes. So retransmission schemes are essentially there to safeguard against the effect of errors. And in all of these retransmission schemes, there is always a balance between latency and overhead. Okay, ideally you want low latency and low overhead, but it's not always possible to obtain this balance because latency means delay. Okay, so if there is errors and you got to go back to the transmitter and ask them to send that frame back again, there's a lot of delay involved in that. Okay, the way to reduce latency is to put extra bits that are used for error control purposes, but that has an effect of increasing the amount of overhead. Okay, so there's a balance between latency and overhead, and ideally what you're trying to achieve is a certain amount of reliability for data transmission on a particular link. So in LTE supports a two-layered retransmission scheme. So the first retransmission scheme is referred to as a fast hybrid automatic repeat request scheme, or HARQ. So this one is slightly in between forward error correction schemes and backward error correction schemes because what the HARQ protocol does is it does transmit some overhead. It does give the receiver some redundancy information that enables it to correct very simple errors. So if there are very simple errors in the data that is received, maybe if 1 or 2 bits are in error, maybe it has the capability to correct those errors. But if the receiver says I cannot correct the errors and comes back, then the HARQ provides additional redundancy information. So instead of just transmitting the whole frame again, it provides additional redundancy information, and this additional information is then used by the receiver to correct this. So basically what you're doing is, if that's the data that you'd send, okay, maybe with that amount of overhead, when that is received at the receiver says I can't figure out what the error is, the HARQ will maybe send some more additional redundancy information, and the receiver tries to work out if it can work out the error that was in that frame that was received. Obviously, if both these fail, then it has to use some other mechanisms. So this HARQ protocol is referred to as a lightweight HARQ protocol. The next retransmission scheme is called selective repeat ARQ protocol. So here in selective ARQ protocol, it's obviously it's a highly reliable one, but it is a more slower one, okay, compared to the HARQ, which is a faster one, but not as reliable as the selective ARQ one. So in this one, the ARQ protocol provides a means of completely retransmitting packets that the HARQ protocol could not correct. So if after this additional redundancy bits are received by the receiver, and the receiver cannot still correct the error, then it goes up to the selective repeat ARQ protocol, and that one just retransmits that entire frame or packet that was in error. So it's more expensive in terms of latency and overhead, but obviously it's more reliable. Okay. So in LTE, both HARQ and ARQ protocols are terminated in the base stations and in the mobile equipment, which gives tighter coupling between these two. So these protocol stacks are all in the node B, and the LTE. Okay, so it's not like in some of the mechanisms where some of the error control could be done in the RNC, for example. Okay, so the further away you put some of these protocol stack from the radio transmission link, the harder it becomes to control the whole process. Okay, we also talked about this business of multiple antenna transmission. So we can have multiple antennas. We can either have one transmit antenna and one receive antenna, or two antennas at the transmitter and two antennas at the receiver, or either 2 or 4 at the transmitter or 2 or 4 at the receiver. Okay, basic idea behind MIMO. So these multi-antenna transmission systems can enhance the system performance, and these LTE multi-antenna can be divided into two types. The first type is called transmit diversity. So what happens in transmit diversity is that when you have multiple antennas, you can use a technique of averaging the signals received from these multiple antennas and avoiding deep fading that occur in antenna. So when you notice that the signal from one antenna is going through a deep fade, you avoid the signal from that antenna, and that way you can take the best signal, or you can take the average of the two, and so forth. So this transmit diversity can be used for downlink control channels, because it's very important that you receive downlink control information as accurately as possible. And it can also be used whenever you transmit real-time user data transmission, because with real-time user data transmission, you don't have the flexibility of going and asking the transmitter to retransmit it. So if there was some other mechanism that you can use to get a better real-time user data signal, then transmit diversity would be one of them. So transmit diversity, apart from improving the quality of the link, it can also be used to increase the system capacity and also the range of the cell. Because sometimes if you just have one antenna and one receiver, the range of the cell could be small. But by using two antennas and two receivers, you could go further and still have possible communication. Okay, so you're increasing the range of the cell that you can have. Another possibility is called multi-stream transmission, including beamforming. Okay, so these are concepts that come from MIMO. So here what you're doing is you're employing multiple antennas at the transmitter and the receiver to provide simultaneous transmission of multiple parallel data streams over a single radio link. So what you're doing is, say you've got 4 antennas at the transmitter and 4 antennas at the receiver, and you've got some data coming in. You take your data and divide it into parallel streams and transmit it across these 4 antennas. And this is referred to as parallel transmission, multiple parallel data streams over a single radio link. And this is also intended to improve the system performance. Remember, one of the slides I showed you earlier was that by using these MIMO concepts, you can get higher data rates in both HSPA as well as in LTE. Okay, the other important thing that is also noted here is in lightly loaded cells or small cell deployment, multi-stream transmission yields very high data rates and makes more efficient use of radio resources, whereas in large cells which have a heavy load, it does not make much of a difference. Okay, so here's a diagram which shows okay, so basically what we are trying to do with these multi-antenna advanced antenna solutions is to improve the performance of your LTE network in terms of the peak data rate that you can get. Okay, we saw in the earlier slides that the peak data rates increases by a factor of 2 or factor of 4 based on the number of antennas that you use. We can improve the coverage by increasing the maximum distance that you can have between the transmitter and the receiver. And you can also increase the capacity by increasing the maximum number of users that can be simultaneously supported. Okay, so I think we're going to take a break here now, and we'll come back after 10-15 minutes and carry on with LTE network architecture.